previous lecture, we had been looking at vectors, in particular how to represent them algebraically, and then we looked at the product of vectors and defined a scalar product which we wrote as A x b x plus A y b y plus A z b z, and a vector product which gives me a vector A cross b and in a short way I wrote this as determinant of A x, A y, A z, B x, B y and B z, and I had asked you to check that this gives the correct answer. We define these two products in this manner because they satisfy certain transformation properties of vector components under rotation. Let us look at these products now slightly more carefully. So, let us look at the dot product A dot B, which is A x B x plus A y B y plus A z B z. This can also be written as magnitude of A times magnitude of B times cosine of theta, where theta is the angle between A and B, and theta is the smaller of the angle. So, theta is less than 180 degrees. In particular, if I look at the unit vectors along x direction, y direction and z direction, we find that I dot I is same as j dot j, they are all equal to 1, because their magnitude is 1 and the angle between j and j or k and k is 0. Similarly, I dot j is 0, so is j dot k and so is k dot I. Notice that the dot product or the scalar product can be both negative and positive, because cosine theta can be negative or positive. Similarly, if I look at two vectors A and B, then A cross B, which I can write as the determinant I j k A x A y A z B x B y B z is also equal to magnitude of A times magnitude of B times sine of theta, where theta is the smaller of the angle between A and B. So, theta is less than 180 degrees times a unit vector in direction n, where n is perpendicular to both A and B. So, it is perpendicular to the plane formed by A and B. So, it will be somewhere like this, maybe coming out of this plane of the board. How about whether n is this way or this way? This is answered by the right hand rule. You turn A towards B through the smaller of the angle, and the thumb gives you the direction of the vector product. So, in this case n would be going down. You can see that A cross B is going to be equal to minus B cross A, because the magnitude will remain the same, but the direction of n would change, because now you will be turning B towards A. This is also clear from the components if you look at them carefully. So, this is how the cross product works. In particular, if I look at the unit vectors I, j and k in x, y and z direction, then I cross I is 0 and so is j cross j, because the angle between them is 0, and so is k cross k. On the other hand, I cross j is equal to k, j cross k is equal to I, and k cross I is equal to j. These are the relationships between unit vectors. Let us now look at one or two examples where you see these relationships carefully. First, I want to show you that A cross B through an example is really equal to A B sin theta times n, where n, as I told you, is in the sense of rotating A towards B through the smaller of the angles. So, let us for simplicity take this as x axis, this as y axis. Consider B to be a vector, unit vector in x direction. So, B is equal to I, and consider A vector to be in this direction, which is 45 degrees from the y axis or the x axis. So, A is equal to minus I plus j. You can see that the magnitude of A is square root of 2, magnitude of B is 1, and the angle theta between them is 135 degrees. So, therefore, A B sin theta n is going to be equal to sine of 135 is 1 over root 2 is going to be equal to 1 times n. Turn A towards B through the smaller angle, and that gives you a direction the opposite to z axis. So, this is going to be minus k. Let us see if you get the same answer if I explicitly do component wise vector product. In that case, A cross B would be minus I plus j cross I cross I is 0 and j cross I is minus k. So, you see both give you the same answer. Now, I want to demonstrate to you that A cross B gives you a vector that is perpendicular to both A and B. Since A cross B is equal to modulus A modulus B sin theta n, where n is perpendicular to both A and B, that means that A dot A cross B, which is equal to modulus of A cross B cosine of theta, let us call it theta prime, because now this is the angle between A and A cross B, should be 0, because A cross B is in a direction perpendicular to A, and so should be B dot A cross B, which is equal to modulus or magnitude of B, magnitude of A cross B, cosine of, let us say, theta double prime. Again, since A cross B is supposed to be perpendicular to A and B both, this should also be 0. So, let us take an example. Let us take A to be a vector, let us say 2I plus 3j plus k, and B to be a vector, let us say minus 3I plus 4j minus 5k. We want to take the cross product or vector product and show that the resulting vector is really perpendicular to both A and B. So, what we will do is we will calculate A cross B and then take dot product with A and take dot product with B. So, let us do that. So, A cross B is going to be equal to I j k. Let us see what the vectors were. 3 2 3 1. So, 2 3 1 and minus 3 4 and minus 5, minus 3 4 and minus 5. So, the cross producted I minus 15 minus 4. So, minus 19 plus j minus 3 plus 10. So, plus 7 plus k 8 plus 9 17. So, this gives me a vector minus 19 I plus 7 j plus 17 k. This is A cross B. Let us take A dot A cross B, which is equal to 2 I plus 3 j plus k dotted with minus 19 I plus 7 j plus 17 k. Now, I can use the distributive property and show that I dot I is 1. So, this is going to be minus 38, I dot j is 0, I dot k is 0. So, no contribution from here, plus 3 would multiply only the j component plus 21 and k would be plus 17, which is equal to 0. Since A and A cross B both magnitudes are non-zero, this can only happen if the angle between A and A cross B is 90 degrees. I leave it for you to show that B dot A cross B is also 0. Thus, we see that A cross B is perpendicular to vectors A and B both. Let us now look at geometric interpretation of a cross product. Of a vector product. A cross B magnitude is nothing but magnitude of A as magnitude of B times sine of theta, where theta is the angle between them. So, if there is a vector A and there is a vector B, an angle between them is theta, you can see that A cross B is nothing but A times B sin theta. This is B magnitude. So, this is B sin theta. So, this is the base times the height of this parallelogram, and therefore, magnitude of A cross B is the area of a parallelogram formed by A and B. Next, we look at A cross B dotted with C. This I leave for you to show that is AX, AY, AZ, BX, BY, BZ and CX, CY and CZ determinant. Its value is equal to this, and this has a geometric interpretation of, if I form a parallelepiped by vectors A, B and C, it is the volume of this parallelepiped. So, that is the geometric interpretation. Since I can write A cross B dot C as this determinant form, this also shows, since determinant does not change if I change its rows twice, this is also equal to A dot B cross C. This is also equal to C dot A cross B, which is same as this. And there is one more term, this is also equal to B dot C cross A. All these are equal. This is cyclically the dot product and cross product go like this. So, this is a general review of vectors that we have done.